Hey Ramblers, this video covers chapter 10.1 in our textbook and it continues our work with circles. Now the book introduced circles with 9.2, the last video. So if you need to review any of the topics that were covered in that video, like the definition of a chord, of diameter, or the formulas for circumference and area, I'd ask you to do so because it's kind of assumed that you're comfortable with those to understand this video. We're going to go through a couple more pieces of vocabulary and then move into three theorems, two of which are the converses of each other, which means they're biconditional, and the third, which is really just a lemma. It's almost a direct extension from the first two. So please take good notes, pause when you need to, and I hope this helps you. Okay, in addition to the vocabulary we covered in the 9.2 videos, I want you to know what concentric circles are. Concentric circles are two or more coplanar circles with the same center. Okay, coplanar means that they're on the same flat surface. And having the same center means that, well, like these two circles there, they have the same center, O, and so they are concentric circles. I could make another one, and you start to get this bullseye look. Those are all concentric circles. All right, what does it mean then to be congruent circles? Well, congruent circles just have the same radii. They don't have to be in the same position, just like triangles. If they have the same radii, then or congruent radii, then they are congruent circles. All right, let's finish by talking about what the circle interior is. The circle interior is the distance that is from the center that is less than the radius. So both of the new circles that I created would be in the interior of the circle, and they would be in the circle interior. But if I came along and made another circle, that circle with M on it would be outside the circle interior. Okay, not a terribly difficult topic, but I do want to emphasize that the only thing that is a circle is these ring of points. The circle interior, kind of the shape that most preschool kids would refer to as a circle, is what's referred to as the circle interior. Okay, let's move on to the theorems. Okay, there are three theorems in this section. But before we start investigating any of them, we have to be clear on one more definition, and that is the distance of a chord to the center of a circle. Okay, we see that the distance from a chord to the center of a circle is the length of the segment perpendicular to the chord. All right, well, why? Well, we can see that the measure of angle OEA is 90 degrees. So in other words, OE is perpendicular to AB. And that's got to be the way it is. Because let's take a look at another example. Suppose we had another segment drawn from O that was to AB but not perpendicular, like this segment here. This segment is OF. Notice that as I manipulate point F, the length of the segment OF changes. So that's not a very good standard for what we call the distance from a chord to the center. So it's only when the segments are perpendicular that I get the actual distance. And as you can see, OF now is equal to OE because it is now perpendicular to the chord. Okay, let's move on to the three theorems now. Okay, Theorem 74 tells us that if a radius is perpendicular to a chord, then it bisects the chord. So a line coming from the center must be, if it is perpendicular to a chord, then it bisects it. Well, let's take a look at it because that's kind of what we had when we looked at the definition of distance to the center. So this line, or this segment OE, if I extended it to the circle, would be a radius. So why don't we work with that? Let's just get rid of the text here, and we'll work with OE with the intention that we could be extending it all the way to the circle. All right, so I'm also going to draw in OA and OB as auxiliary lines because I'm going to need those. Now, since OA and OB are radii of the same circle, we know that they're congruent. OE is congruent to itself by the reflexive property, and since I know that this radius OE, or part of the radius OE, is perpendicular to AB, then it must form two right angles there. So that makes triangle OEA congruent to OEB by hypotenuse leg. Therefore, AE is congruent to BE by CPCTC, and so OE must bisect AB. All right, it's not really important that you are able to run through that proof again, but it's really important that you recognize when a line from the center of a circle is perpendicular to a chord, it bisects it. All right, let's move on now to Theorem 75. Theorem 75 tells us that if a radius of a circle bisects a chord, then it is perpendicular to that chord. So if a radius, like again, OE is part of a radius, but let's assume that it goes all the way to the circle. If this bisects AB, then it must be perpendicular to that chord. Let's take a look at the proof. Once again, if we draw in OA and OB, we know that those two segments will be perpendicular because they're radii of the same circle. Then EO is congruent to itself by the reflexive property, and we know that OE bisects AB because that's given. So therefore, these two triangles are congruent by side, side, side. We can show that this angle here, OEA, is a right angle, as is OEB, because they're congruent through CPCTC and supplementary. So we've proven that if a radius of a circle bisects a chord, then it is perpendicular to that chord. Okay, let's take a look at one more theorem, but we're not going to bother proving it because really it's so self-evident. So give me a minute to clean up the diagram. Okay, Theorem 76 tells us that the perpendicular bisector of a chord passes through the center. Well, we've just shown that if radius from O through E bisects the chord, then it's perpendicular. And we've shown that if a radius is perpendicular to a chord, then it must bisect it. So this really does follow, kind of as common sense. But let's take a look at the summary of what the information I want you to know from this section. So in summary, if a radius is perpendicular to a chord, then it bisects the chord. And if a chord is bisected by a radius, it's therefore perpendicular. So these two things are, these two theorems are converses of each other, which makes the statement biconditional. So whenever you see a radius perpendicular to a chord, please know that it bisects it. Or if you're given that a radius bisects a chord, know that they're perpendicular. Okay, thanks for watching. I'll include a couple of tutorials to help you through some of the problems that will come up in the exercises. Thanks, Ramblers. Okay, in this example, I want to find the distance from the center of a circle to a chord that is 80 meters long. It's a very long chord. If I know that the diameter of the circle is 82 meters. Well, if the diameter is 82 meters, that means that the radius is 41. And if I draw a line from the center of a circle perpendicular to a chord, I know that it will bisect the chord. So what was 80 will now be 40 and 40. So I have a right triangle with the legs of 40 meters and x meters, and I'm looking at a radius of 41. So I simply solve for this triple, x squared plus 40 squared equals 41 squared, and hopefully you remember that x, or 9, 40, 41 is one of our triples, so x must equal 9. That's pretty much the way to do all these problems. Set up a right triangle using half the length of the chord, your radius, and the distance from the center as your three sides. Okay, hope this helps. Number 22 in the book. It's kind of a complicated problem. It asks us to find the radius of a circle in which a 48 centimeter chord is 8 centimeters closer to the center than a 40 centimeter chord. So I've drawn the picture below, and it doesn't look like much. Well, a common approach with these problems is to make a right triangle. So when I draw the line from the center at O to each one of the chords, I'm going to draw a line perpendicular so that it bisects it. Now we know that in the first triangle, the chord is x centimeters away to a 48 centimeter chord, so when I bisect it, it'll become a 24 centimeter chord. We don't know the radius, so we'll call it r. In the other triangle, we're going to be x plus 8 units away from the center. The radius will remain r, and the length of the chord is 40 units. So 40 divided by 2 is 20. So in order to solve these two variables, we're going to need a system. Using the Pythagorean theorem, I can set up these two equations, and since they're both equal to r squared, I'm going to set them equal to each other. Luckily, the x squareds cancel out, and I can solve for x. I'll have 16x equals 112, and so x equals 7. That's the distance from the center, but that's not what they asked us for. They asked us for the radius. So I'll plug 7 back into one of my triangles, and I see that I have a 7, 24, 25 triangle, so the radius is 25.